Did everybody already get their pumpkin spice lattes?
That's funny. Is that what you were talking about in the group me? Is that why? Um, the friend that I'm staying with right now, she is at Starbucks because she wanted pumpkin spice, and uh, she also just wanted to smell it, so she's gonna hang out there for like an hour. Yeah, and yeah, Joseph's girlfriend did good.
I have a question about Alex.
Yeah,
Alex.
go for it.
So when does that due? Or what's due on
When
Alex?
Okay, so in Alex, there are many assignments, right?
Okay.
The first, so each section that we do, each notes like that I go through, there'll be a homework assignment associated to that notes section.
Mhm.
Um, and so far we've done like what, two or three, let's call it sections of notes. There's going to be a homework assignment for each, and they'll be labeled like in Alex as like homework, whatever. And the first set though, I made them as kind of, at least for this section, which I might have to go fix the rest, but I put them as like a set, and they're all due. The first two from last week that we did are due September 4th, which is that this Sunday? Yeah, I think I picked Sundays like to make them due. So the material we cover in the week will be due on Sunday. Um, Typically I tried to like be consistent, but I totally could have messed this up. And so your first assignments aren't due until Sunday. And then the stuff we do this week, I might have also made it due this Sunday, because typically I think I gave like a week lag for the first week for people who add drop or anything like that. But typically everything we cover like this week would be all due on Sunday. Instead of making it due like the next day after class, which is the norm. So for those of you just joining, Miguel had asked like what for the homework, what is due in Alex, and the assignments that are due. Again, Sunday's the first due date, but typically whatever we go over, that's like, if we do 5.1, your homework is on 5.1. And I mean, traditionally it would be due like before the next class. So like today is Thursday. Wait, is today Thursday? Yeah. Today is Thursday. So it would be due on Tuesday before class. But instead, and then like Tuesday's homework would be due Thursday. So instead, what I decided was the whole week's worth of material, I open it up to you like the week we start it, and it will be due that Sunday. Now, if for some reason this is an issue, or people would rather, whatever happens, I mean, email me, let me know. Because I don't have I don't particularly care when it's due. It just needs to be done, before we go too far. And then you have 10 homework assignments due on one day. Like that wouldn't make sense. And you just want to make sure you're doing these homework assignments prior to the exam, so that like maybe what you need to study more or less, right? So Miguel, hopefully that answered your question.
Thank you.
Yeah. Okay. And as for the review in Alex, there's like review assignments and sections and all this. If you're not doing it, I mean, if you need the help with math, maybe try it. But it is not graded. Do not stress about it. It might annoy you that it's there. It won't go away, right? Like, yeah, unless you complete it. But I mean, it's not, I wouldn't stress about it. It's not a big deal. It's just, it was in case you had time beforehand. I mean, most people probably say, oh, you really should do it, it's mandatory, but it's not graded. It's just something so that, like if you're behind in mathematics in general, that review, like you should kind of know what's going on there. And so maybe it's more of a refresher, or maybe you do have to kind of catch up and teach yourself some things. And that just means that the course might seem a little more difficult. But so in any free quote unquote free time that you have, right? Because we all have so much free time. But you could always work on it, right? Okay.
Talking about the Alex,
The review.
the review, the one like the algebra, like
Yes.
geometry and all that. Okay. Okay.
So it is not graded. It is not due. Like, don't stress. I mean, I think there is a due date. It's like September 11th or something. I don't know why. Again, the program coordinator creates these assignments, and I actually can't really control that. or I'm not supposed to change anything. But yeah, so those review assignments, they're just really for your help, for your benefit. If you can do them, maybe it's a little confidence booster,
Yeah.
if not, maybe it means you'll have to study a little more, and there are so many resources at like at the learning lab and all of these things. So I would just recommend that if you do need help, definitely go, like, do those types of things. I'm going to start sharing my screen so we can get started here. Okay. Also, just a quick reminder that please check attendance, because I entered it late the other day because I was a mess. But just make sure maybe at the end of each week or at every exam or something, you keep track of what classes you are at, because sometimes I have the Zoom record, so I do have it. But if I'm looking real quick and I'm like, oh, these 3 people are absent, and I mark, and God forbid you weren't the one and I mark you absent, if you care, then just send me an email and let me know. That's totally fine. Okay, sorry, you're not seeing anything here. So this was okay. Now, hopefully you are. So we left off here at the end of the 5.3, 5.4a notes. And we're just going to finish off this example. And I think I have to every time. I already forget how to hide my, oh, look at that. Okay. Oh, good. This is all set up for me. All right. So
Can you
so
make
I
it
think,
full screen? I'm sorry.
oh, yes. Okay. And it's, yeah, switch. Thank you. Every time, remind me, because I don't know. But yes, this is perfect. So we're going to do this problem here, and let me make sure I have the chat. I have everything up. So, okay, hopefully we're good to go. Again, stop me if there's questions. And it depends on how today goes, but we might actually have some time for more questions at the end if you did have like some Alex questions or just in general. Okay, so we went over this, the Pythagorean identities. We went over that last time. The sine squared plus cosine squared equals 1 is really the most important one, right? And then using these fundamental identities, we're going to determine if these expressions are true or false. If it's false, provide a counterexample. That just means if it's not true, plug an angle in and it probably isn't going to work, right? Or find one that doesn't work. Okay, so looking at this first one, we are going to, sine of theta, I think we're going to keep the same, but I know that cosine of pi over 2 minus theta, this, we can use a cofunction. And so the cofunction of this is sine of theta, right? So pi over 2 is 90, remember. And if you scroll up, I think it's in a chart somewhere. Oh, geez, now it's too far up. But we did this. Oh, man, maybe it's not even in this one. We did this somewhere. And we have the cofunctions, and we know that sine of theta is the same thing as cosine of 90 minus theta. And pi over 2 is 90 degrees, right? So this is the same thing. So therefore, we can bring this down, sine theta, and then we can change this to be also sine theta, right? It's the same thing. And then I have equals 1 minus cosine squared theta. I'm just going to keep that the same as well. But keep in mind, based on this up here, right? This, based on the trig identity, so I'm going to write trig identity, this is equal to sine squared theta. And would you look at that? If I multiply these, this is sine squared of theta. So these are equal. This checks out. This is going to be true. And what that means is for any theta we plug in here, it should be equal on both sides. The left side looks way more complicated, right? So I'm not interested. Now for the next one, we're going to do something similar, but we'll start with tangent. Typically, if you're asked to do something like this, I try to make everything in terms of sine and cosine. Oh, and David has a question. How did you make cosine equal to sine. Like, what did you convert it to? So for this, we converted because it's cosine of, here we go, it's cosine of pi over 2 minus theta. That means 90 degrees minus theta. If I only use theta, that's why I was allowed to switch it to sine. So I used this co-function identity, and maybe I should have written co-function identity. And this is in the previous notes. There's like a table of co-function identities, or maybe we made it ourselves, but we said that cosine, or we would say sine of this is, okay, so this is yes, I see what you're saying. So it would be sine of alpha, but in this case, alpha is, okay. I see what you're saying. But yes and no, because, so say this was theta and we have sine of theta and this is alpha, right? We know that sine of theta is cosine of alpha, but I gave you this. I gave you pi over 2 minus theta. So it's kind of like this angle right here is my alpha. So that's why I was able, because if you think about it, remember that theta plus alpha equals 90 degrees. And so alpha is 90 degrees minus theta. Oops, that's a bad theta, but or that's the same thing as pi over 2 minus theta. So so hopefully, sorry, multiple people were commenting here, but Victoria had commented on the sine of alpha. So technically, this statement is kind of like sine theta times cosine alpha, and we just were able to change it. Oh, so that is unique to pi over 2 minus theta. Yeah, it is unique to that. Yes. Okay, so hopefully that is clear. Are they because equal? I don't understand that question. You could unmute if.
I meant the sine and the cosine in the parentheses pi over 2 minus theta. So are they equal? That's why you made a sine theta times sine theta.
Yes, they are equal. And that's because, like, if you look at theta in this triangle that I drew, I'll kind of talk about this. So if you look at theta, we have this, looking at theta specifically, this would be the opposite, this would be the adjacent, and this would be the hypotenuse, right?
Sorry. I just saw the green. Green.
Oh, you just saw the green stuff? Okay.
Yeah, my screen.
Yeah. And so this, if we look at alpha, like this is the opposite, this is the adjacent, and this is still hypotenuse. And that's why sine of theta is cosine of alpha, which is also pi over 2. Alpha is also pi over 2 minus theta. Yeah, there's a lot connected here, so it can get really weird. I guess it can seem weird, but it's actually just all connected, and that's why this works kind of nicely. Okay, if there are more questions with that, feel free to type in the chat and we can come back to it. But let's look at part B. So like I was saying, when I want to do something like this and check that something is equal, I always try to make everything sine and cosine, because that's just, well, to me, that's easier. But sine and cosine, we know sine and cosine very well. We don't know the other trig functions as well. And maybe you do, but I definitely don't. So I'm going to change tangent here to sine over cosine, sine theta over cosine theta. And yes, there was a question, Joseph. This is the last page. This is where we left off in 5.3 and 5.4a. So this is the very last page of that. We just have this one problem, and then we're going to switch to 5.4b, which is the next set of notes for today. Yeah. So I have sine times cosine. Then I have, or sine over cosine. Then I have times cosine. I just bring this down, theta, equals, I'm going to keep 1 minus cosine theta. I'm going to keep that the same for now. So now I can see here, well, these cancel out. Cosine theta over cosine theta, that's 1. And then I'm left with, let's go here. I'm left with just sine theta on this side. And I have equals 1. I can't really simplify 1 minus cosine theta. I don't know. And okay, I'm trying to figure out if this is true, right? I don't really know, right? So I'm writing equals, but we're trying to figure this out. And so is this true? Well, this would tell me if I wanted to rewrite it. I mean, if you're not convinced yet, yes or no, then if I wrote sine theta plus cosine theta equals 1, well, I know that if they're squared, this is true, but that is not the same thing. So this is actually not going to be true. So this is going to be false. And if it's false, we need to find that counter example. So I'm going to pick an angle. And I mean, if it doesn't work, it most likely shouldn't work. But so I'm going to just pick, and you can try another angle. Try angle theta equal to, I'm going to pick pi over 6, which is 30 degrees. I mean, I think you could also pick pi over 4. You could pick, yeah, you could pick really anything, but I'm going in radians here. You could also do it in degrees, right? But so I'm going to try this angle. So I'm going to go back and see. I'm going to just start. The easiest one is this. So I'm going to see if this is true. Sine of pi over 6, is that equal to 1 minus cosine of pi over 6? And it looks like, okay, maybe this will work, but let's see. So sine of pi over 6, I know this from my right triangle and from my unit circle, but it's just 1/2. And then 1 minus cosine is the root 3 over 2, right? This is the one where one of them is root 3 over 2, one of them is 1/2. And this is definitely not true. 1/2 is not the same thing. 1/2 is only the same thing as 1 minus 1/2, right? So this is not true. So this counts as our counter example. Okay, and I want to save this. Now I have to remember how I do this. Done. Saving. Okay. Uh-oh. All right, let's just double check that that's saved. Yeah, okay, yay. All right, so this is done. Okay, so now we're gonna go, okay, hopefully everybody was good with this. But I'm gonna move on. Let's see. So we are now gonna start the 5.4b notes. So let me go into my drive, into here, into my class notes. And these should be posted. It's either at the end of, or in the middle of the unit 1 bundle, the big packet, or it is posted separately. Okay. So here we're still talking about trig functions. We're still looking at unit circle type stuff. But first, what we're going to do is talk about domains of these trig functions. And then we're going to start looking at graphs of them. And I think the homework gets into this a little bit. Okay, so the question is, at what value on 0 to 2 pi are sine and cosine functions equal to 0? Well, they're only going to be 0 on somewhere on the x-axis or the y-axis, right? So I'm just going to create points here. Like, let's call it, this is 1, 0. I'm going to try to make them even. This is 0, 1. This is -1, 0. And this is 0, -1. And if I'm looking at the unit circle, okay, this was not perfectly even, but I'm just going to, the unit circle is something like this, right? Pretend it's a really nice perfect circle. So keep in mind also the angles that we have here. I'm going to go in radians, but 0, pi over 2. This is just pi. And this is 3 pi over 2. Okay. And then 2 pi if we go full circle again. So from the last class, we discussed that looking at this t to some point here where we have like x comma y, from last class, we learned that cosine of t, oh, I didn't write t. Let's see if this is t, which if I made a triangle here, like the angle is the same, but we're not, we're not so concerned about that. But cosine of t is going to equal our x value, and sine of t equals our y value. These correspond, right? And we saw that last time. And so on the unit circle, which it's a unit circle because one unit is the radius. So the distance from the center for everything is 1 unit, for everything on the circle. And so we want to figure out where sine and cosine are 0. So clearly we can see the 0 here, there's a 0 here, 0 here, and 0 here. These are going to be the 4 places. And let's see which one is 0 where. So for example, just starting at the beginning, change to my pen. Just starting at the beginning, this is the y value. So this is sine. So sine, and then I'm looking at the angle. This is sine of 0 degrees or radians, same thing, is 0. Then if we continue up, I'm at pi over 2. This is cosine of pi over 2 is 0. Then I go back to sine because I'm on the y. Sine of pi is 0. And finally, I'm back to cosine of 3 pi over 2 is 0. Right? So these are all of the places, so to answer this question, at what values on 0 to 2 pi, the values are at 0, and we're including 0, we're not including 2 pi. So we could, sine of 2 pi is 0, but we're not including that one. So we have, 0, pi over 2, pi, and 3 pi over 2. And notice, well, they're never 0 at the same time, right? That isn't going to work, but these are when they're 0. And now this is saying number 2 says generalize to all real numbers. So what this means is, remember how before we talked about if you have an angle, and I'm going to erase this in a moment, but if you have an angle and it's here, you could also say the same angle goes a full revolution and then back, and it's there. You could also say, this is the same angle as going around and around and around like a crazy person. You're spinning 100 times. But if you end up at that, whatever that is, 100-degree angle, you're still at, that's your reference angle. You're still there, right? I could spin around 10 times. And if I do full 360 degrees or 2 pi radians, I'm still going to be facing my computer, right? I'll be dizzy and maybe nauseous, but I'll be facing my computer, right? So what that means is that if sine of 0 is 0, then if I add 2 pi or 360 degrees, I'm still 0. Sine is still 0. I go again, still 0. So there's infinitely many places where we have this, right? Same thing. Well, notice how sine of pi is also 0. So I could say sine of 0, then sine of pi, then sine of 2 pi, then sine of 3 pi, and 4 pi, then 5. I can keep going forever, and all the pies in the world, and my sine will still be 0. So if we generalize this, we're going to say that sine of t equals 0 for t equal to n pi, for any integer n. Oops, let's fix that. Integer n. And what this means is, like I said, you could have 0 pi, you could have negative 5 pi, or you could have 6 pi. Like any numbers of pi, sine's always going to be 0 there. Now, cosine's a little more tricky because of that pi over 2, because for cosine, we have pi over 2 and 3 pi over 2, right? So it's a little more tricky. So cosine of t equals 0 for t equal to pi over 2 plus n pi. Because I'm still adding, if you look at this, I'm starting at pi over 2, and I'm still adding pi, 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 pi. I'm still adding like 1 pi, 2 pi, 3 pi, or negative pi's, right? But I start at pi over 2, not at 0. I'm starting at pi over 2. Now, another way to write this, if you wanted, so I'll put or, we could write this as 2n plus 1 times pi over 2. If you wanted to write it as one big fraction, a bit silly, but we don't normally do that. And this is for any integer n as well. So for example, we can't have, oh, what's the n again? Yeah. Oh, sorry, I didn't clarify that. So Victoria, thank you. I didn't finish my thought there. And here, yeah, we couldn't have, like, I say integer because we couldn't have like 6.7 pi. That's not going to work. That's going to bring us somewhere else on the circle that's not on the x or y axis. It has to be exactly pi that we're adding, or some multiple, some integer multiple. Okay. And hopefully that answered Victoria's question. She had asked what's n again, but yeah. So what functions are undefined? Okay, so now we're looking at undefined. This means divide by 0. So so undefined when sign is 0. Well, this means that if sign is 0, 1 over sine t is going to be undefined because 1 over 0, so this means, or maybe I should say, when we have 1 over 0, this is undefined, right? And so 1 over sine, if you don't remember, here's your hint to remember, it's cosecant. So cosecant is undefined when sine is 0. And what else? Because there's something else when sine is in the bottom. So we can put cosine in the top, right? So cosine over sine is actually cotangent. Ooh, and I hate t. They switched theta to being t because we talk about like integers and stuff. But if this looks confusing, I'm sorry. I should try to make my t's look all weird. But so this is going to be cotangent. And so the places undefined when sine is 0 are cosecant and cotangent. And then we're going to do the same thing for cosine. So for this one, we know 1 over cosine will be undefined, and that's the same thing as secant. And then we know sine over cosine will be undefined, and that is tangent. So again, undefined when cosine is 0 is secant and tangent. And now we're going to fill in this fun little chart. Lots of charts for you guys in this class, I guess. So they're giving us the function on the left-hand side. Then we have undefined at. So we want to see, because thinking of the graph, if we are going to graph these eventually, and think of their properties, if the function's undefined, we want to know this. We want to be aware. So sine and cosine, sine and cosine are never undefined. So I'm going to use a more fun. Okay, so sine and cosine, never undefined here, okay? Which is pretty cool. And their domain is all real numbers. Which we write this as this capital R with like a double bar. So when I'm feeling extra lazy and don't want to write like all reals, I will just write that double bar. What does your tan t stand for again? Tan t is tangent under question B. Yeah, so tan t is just tangent of t. Yep. Okay, cool. Thanks, Miranda. Okay. So now we have our function. We go from, so we're good with this first one. Now we have tangent and secant, and they're basically giving us the ones that are related here. That's why. So tangent and secant, as we could see from this problem here, right? They are both undefined when cosine is 0. And then if we go up even more, cosine is 0 when t is pi over 2 plus n pi. So here they're undefined at pi over 2 plus n pi, where n is an integer, right? And the domain here is going to be everything except for wherever that's undefined. So we need to figure out, so that's all we're gonna have to say. So the domain, I'm gonna write, is all reals except, and it feels a bit silly to say this, but this is how so many mathematicians say, like they'll say all these numbers except, it's like, okay, well, then it's not all the numbers, but yeah, all reals except pi over 2 plus n pi for all n, so for all integers n, right? Or there is another way, I don't like how that looked, there is another way that we can write this in, it's called, I don't know if it's interval notation or it's some type of function notation. Yeah, exclude odd multiples of pi. Yeah, it's basically the odd multiples of pi over 2, right? Because if you add, it's like 1 pi over 2, 3 pi over 2, 5 pi over 2. Yeah, exactly. Because if they're even, for Jakob, he said exclude odd. You could also write that, but if they are even, then it's not undefined, right? Because they're
I
like,
just mentioned that isn't the book.
oh, I see. Yeah. And you could also write it that way. So that's good. And yes, set notation. That's probably what this is. Thank you, Michael. So we could write or t such that, so this is the domain. T, and this line means such that, how that came to be, these crazy math minds, such that t is not equal to pi over 2 plus n pi, and I'll write again for any integer n. And then we do these curly braces, and this is our notation if we wanted to say like a nice little set, right? I'm not going to be picky about how you tell me the domain. If I want a specific way, I'll let you know. But for now, I just want you to tell me and get it correct, right? Like in Alex, they might tell you, like they might show you how they want it entered. And then last but not least, we are going to have, so we did this one. Last but not least, we have the cosecant and the cotangent, or cotangent and cosecant, right? And that's when sine is undefined. So this is undefined at just n pi, right? So all integer multiples of pi. And if we write this, again, you could write the all reals thing, but let's try this set notation, right? We're going to do t such that t is not equal to n pi for any integer n. And we're getting really close to seeing, I'm not sure if this happens today, maybe it doesn't, but we're getting really close to seeing graphs of these functions, or at least understanding graphs of these functions. And in order to do so, we're going to talk about periodic functions. So I'm going to get to this next page if hopefully everyone is good, or we will check that off. We did all three. So, and I'll keep it here for a sec while I read this. So periodic functions, a function f, as it says here, is periodic if f of t plus p, so this is just two values, equals f of t for some constant number p. So for example, if p was pi, and every time I add pi, it's the same thing, this is a periodic function, right? Even if it was 2, and every time I add the number 2, for whatever reason, the function is the same thing, this is a periodic function. So then it says here, f repeats at regular intervals. Okay. So the smallest positive value for, p, for which f is periodic, is called the period of f. And this is what we're going to talk about for our trig functions, because all of our trig functions are periodic. And what that means is if we were to graph them, which you guys could just Google it or Desmos it, right? You'll see they either repeat kind of like a heart monitor type thing, or they're just repeated curves in some type of fashion. The curve repeats at some point. And so we're going to kind of take a look at this for sine, cosine, and tangent, which is sine t over cosine t. Okay, so I'm gonna scroll down a little. So what we can look at here, and just keep in mind, like, remember maybe I'll just say, remember the signs that we did this before, where, okay, sine of t was, it was like positive in this axis, positive here, negative here, negative here. Cosine was positive here, negative in the second, negative in the third, right? Because it just represents the x. And then tangent, remember, was positive, negative, positive, negative. It was like opposite, like an x, right? So I'm just writing that for us as we kind of look through, and we're going to fill in this periodic properties of trait functions, right? So if we're looking at something like this, and maybe a point like from t, and maybe we call this, maybe we call it a comma b instead of x comma y, or whatever you'd like to call it, right? If we keep going, so say we keep going here on this, we're first going to look at, this, we'll look at sine, we'll start here, right? And say from here, I just keep going, traversing around the circle. So that's what we're going to look at, right? So say I keep doing that, and I say, okay, oh, maybe I don't want highlighter. I'm going to say, oops. So if this point is a comma b, I know that if I go over here and I reflect over the y-axis, this point, it's still going to be, I don't know what x, like, so, okay. Right, this would be A, and this is B, right? Okay, so what happens is when we reflect this, this actually should be negative A, and B stays the same, right? So we're still, like, as we cross through this, our y value is staying the same here. And again, this just keeps happening as we keep going. So if I reflect this again, and I reflect it like to here over the x-axis, and I kept going around the circle here, I would get, okay, now I'm at negative A, negative B, and then again, I can reflect it over here and get A, negative B, and then go all the way back to the beginning, right? So just keep in mind that when we are thinking about the period, we want to think about when does this repeat? So I see first I have A comma B. Like I start from the beginning, right? I travel around. I have A comma B at this point. I keep going. I have negative A comma B. Then I keep going. I have negative A, negative B. Keep going. A, negative B. And it's not until, so starting from the very beginning, it's not until I go all the way around back to here that I see A comma B again. So that means I have to go one full circle. So that means I need to go around the full unit circle. So 2 pi radians before I repeat a point. And while I was kind of combining sine and cosine here, all we really care, I should have done this a little differently, but all we really care about, oh, and that's too bright. All we really care about is sine. Oh my goodness, I forgot I have to change on the highlighter. Okay, how do I do this again? This, no, it's hold. Yeah, okay. All right, I'm learning, guys, just bear with me. Okay, so all we have to focus on in this case was sine. I was focusing on sine and cosine. So really we only have to see when does sine repeat. And that's the B, that's just the B, right? So I was giving you both. So if we look at cosine, now this can possibly be a little bit quicker, but if we look at cosine, and again, we have this point right here, right? And I say, okay, let's say this is A comma B. Well, we're really only concerned about cosine, so the A. And we can travel all the way around. We can reflect this point, reflect the point, reflect the point, and we can travel all the way around. And if we reflect here, it's negative A. If we reflect here, it's still negative A. Then it goes back to being A. And then we get A again. So what we want is we want like a pattern, and we'll see A, negative A, negative A, A, negative A, negative A, A. So there's our pattern, right? It's like positive, negative, negative, positive, and it'll keep going as we go around. Now, what we see here is that, again, the same thing. You have to go all the way around before you can get the exact same cosine that you got before. One full period. So, so same for cosine as this, right? Before I repeat a point, I'm just realizing I wrote before I repeat a point, before it, I think is what I meant. Before it repeats a point, the function. Okay. Now looking at tangent, this is slightly different because this is sine over cosine. And you can see here, like noticing that we have like plus, minus, plus, minus. It looks like it might just be positive, negative, and then repeat positive, negative, and then repeat positive, negative. And so there is, I mean, I guess maybe it's hard to see, but if we think about, you know, our right triangle trig here, and we think about the X and the Y, like this is the Y, this is the X, right? When I travel, so it's not the same in this second quadrant, it's not the same, right? But if I go here and reflect the point across the origin, and I draw this right triangle, and I basically reflect everything across, this is my X and this is my Y. I mean, they're both negative. But this is going to be the same point as that first point. It's going to repeat here. So when I travel from this point to here, I'm the same. And then I go from this point to here, I'm the same again. So because I'm positive and the next thing is negative. So this actually, this has, we'll say, the same sign every pi, or every 180 degrees tangent repeats the sign, repeats itself. And so based on everything that we just kind of drew here, we can fill in our chart below. So we'll fill this in. So sine, the period is 2 pi, cosine, it's 2 pi. And we basically do cosecant and secant are the same as sine and cosine because they're just reciprocals. So they're also going to be 2 pi. And then tangent and cotangent are similar because they're reciprocals. So their period is pi. And if you're thinking, yeah, like sine waves. Yeah. And if you're thinking like, what is going on here? If you do go into Desmos and graph like sine of X or cosine of X or tangent, right? If you do this, you're going to see there's a pattern and it repeats every 2 pi for sine and cosine. And then it repeats every pi. So it'll look like 6.28, like if you click the point. Yeah. So what this means is the property is that sine of t plus 2 pi actually just equals sine of t. So if we're actually calculating the sine, we might say the angles are not the same. So I might do a full, you know, if I jumped off a diving board and did a 360, like, even though that's the same as 0, I would never want to brag about jumping and going 0, turning 0 degrees, right? Like I want to brag about doing a full 360 or whatever, right? So the angles are not the same, but the actual values are of sine and cosine because we're repeating here the direction we're in basically. So we can say 2 pi for all of these, sine, cosine, secant, and cosecant. And then for tangent and cotangent, I mean, it's just pi. It's just whatever the period is. And so we can just note that, these are all the same period, and these are the same period. So it means those graphs are actually going to all look pretty similar in some type of way when we get there, right? Okay, now it's saying use properties of trig functions to simplify this. So we look at this and we say, okay, tangent of t plus pi. Well, I know just from what we did above, tangent of t plus pi equals tangent of t, right? So this right here is the exact same thing as tangent of t, if we're just calculating. Same thing with cosine. This here is going to match, is just cosine of t. And so we can just write it as cosine of t. But now that simplifies it a little bit. It looks nicer. But I also know that tangent is sine t over cosine t, right? Oh, and my t there, it looks horrible. Sine t over cosine t, not equals, times cosine t. And now, in this particular case, we can simplify even more because this cancels out to be 1. And so our final answer is this actually simplifies to be just sine of t. And sometimes the purpose of this is just that sometimes when you're solving trig functions or problems, it is easier to simplify before you solve instead of say, okay, my t is pi over 2. What's tangent of pi over 2 plus pi? And then multiply. Like sometimes if you could simplify this first and then plug in pi over 2 or whatever angle you have, way easier, right? So how nice is that, right? I guess. Okay. And okay, well, let me pause. Are there questions here? Are we feeling okay? All right, cool. Seems like we're doing okay. So now we're going to talk about even and odd functions. And again, this is sort of related, well, to period, but I'm going to show examples more so for even and odd. Initially, I think of x squared, x cubed, x to the fourth. I think of powers of x because for me, it just makes a little bit more sense. And this is how I initially learned them, whenever high school, college, whenever they were spoken of. I don't know when the first time would be. But so even functions, what that means is that if I substitute in negative x into my function, I get the same value as x. This is why x squared is the most common. Like, so if you want to think of an example, f of x equals x squared, because 2 squared is 4, but negative 2 squared also 4. So what's going on there? So this is an even function. And what that looks like, maybe I'll draw a more negative x, oops, and x. So if I have something like this, and I mean, I'm going to draw maybe something more complicated, or maybe I shouldn't. You know what? Maybe I'll just draw x squared. We'll keep it simple. Because you could have x to the fourth as well, and those look like w's or m's or something like that, and those are even as well. But we'll keep it simple. We'll graph. If I have something like x squared, I mean, it just looks like this, right? And then if this is negative x and this is x, if I drew it exactly accurately, I mean, let's pretend I did, then this value would match up. So like the value for whatever that y value is, this would match up, right? And what this means, like in terms of words, I guess, is even functions are symmetric about or over, I prefer over, but okay, about the y-axis. So if I reflected, or if I graphed this and folded it along the y-axis, it should line up perfectly, unless my graph is horrible, right? Unless my points are all not even or accurate, but it should line up. And then we have odd functions. And for odd functions, what happens here, again, it's kind of nice, f of negative x. So if I substitute in negative x, it's the same thing as if I have negative times f of x times just substituting an x. So we can basically take out that negative and just solve for the initial problem, which is also, I guess, kind of cool. So let's take a look. So my favorite or main example here is just f of x equals x to the third. And or negative x to the third, or however you want to see this. But so I'll draw this for you as well. I'll try to be kind of accurate. So let's see, x to the third might look something like, okay. It might look like this, right? Something like this. And what we're looking at is if I take an x value here and a negative x value here, if this is the y value, this would be negative y, right? Something like that. And now we're going to talk about this in terms of trig functions. Oh, and let me write symmetry. So this is symmetric about the origin. So it's not about the x-axis, it's just about the origin. So it's basically, if you take the origin, which is that point 0, 0 in the middle, and you just reflected it like diagonally, that's what's going on there. That's what an odd function is doing. Okay. So now we're going to take a look at, again, with what this looks like with trig functions. And so we kind of already know a few of these things, but let's just start. Maybe we'll just start with our sines and cosines. So I'm going to start with the even, but we know that cosine of negative t is going to equal cosine of t. I think we had that on whatever slide that was. And so this is an even function. And it's symmetric about the y-axis, right? So when we graph this, it's helpful if you remember these things when you graph, but I mean, you definitely don't need to, like, again, totally have all this memorized. These are just really good things to know, and they're helpful in solving problems later. And sine of negative t is the same thing as negative sine of t. And so this is an odd function, and it's symmetric about the origin. And the reason you can kind of see this better is maybe if we put these points here, this picture, the reason this picture is this way is because if I have a comma b here, right, this would be for negative t, this would still be a, but it would be negative b. So I'm not exactly sure why this, maybe we're pretending this is here. And like this would be negative b, this would still be a, and positive b, right? And keep in mind that, so cosine of t is a, and sine of t is b. And then we can see down below, cosine of negative t, cosine of negative t is still a, but look at what happened to sine. Sine of negative t is negative b. And I'm just looking at like these points here, and remembering that I'm just remembering that cosine is the x, right? Cosine is x, and y is the sine function. Okay, so I'm just remembering that, that's all. And then we can think about tangent. Tangent's a little more complicated, obviously, because it's a mixture of sine and cosine, right? And I am gonna pick another color here. So, no, that was a bust. Let's do this. Okay. Tangent of t, up above here, we know that it's sine over cosine. So y over x, so b over a, lots of letters going on here. And then below, if we look at tangent of t here, tangent of t is negative b over a. And so tangent of t has changed. And tangent is, we'll see, this is going to tell us that it's an odd. And I messed this up. This is tangent of negative t, right? Tangent of negative t. Because I'm focusing here on like these, right? Oh, this keeps on. I'm focusing here on these guys. So the t and the negative t. Okay. And so now we're going to kind of fill these in. So looking at this chart right here, I could rewrite all of these, and maybe I will. Actually, I'm going to, even though this might seem a little tedious. But I know that sine of negative t equals negative sine of t. And so what that tells me is that sine is an odd function. Okay. Then I know that, and maybe I should be like extending all of these for our eyes. I don't know if this is better or worse, but so then I know that cosine of negative t is the same thing as cosine of t based on what we just found. And so that tells us it's even. And then cosecant, oh my goodness, CSC of negative t. So remember, cosecant is the reciprocal of sine. So it's going to also be negative cosecant of t. It's going to be just like sine because it's just flipped, which tells us that this is odd. Secant is going to be just like cosine. So secant of negative t should be secant of positive t. And again, if you can't see, or if you're not seeing that, just remember that secant of t is 1 over cosine. So if secant, or if cosine is the same for t or negative t, same secant will be the same as well. That's where I'm getting that. And so this is also even. And then we have tangent and cotangent, and they're also related, right? If tangent of negative t, like we just saw above, is negative tangent t, then cotangent is going to be the same way. So this is not going odd, even, odd, even, odd, even. It's not perfect. These last two are both going to be odd functions. So notice, not that it's that important, but notice that these secant and secant and cosine are the only even trig functions. The rest are odd. And it's just something to keep in mind when you're simplifying or when you're doing any of this type of work. Oh, sorry, somebody, I missed this. Can you repeat that, what you just said? Okay, I don't know what it was, but it was maybe about cosine and secant. So cosine and secant are the only even trig functions, right? And just what that means is if we're substituting in negative t, like a negative angle here, it's actually the same as if it was positive. Oh, the one, okay. You want me to repeat that? Sorry. So, what I said was secant of t is the same thing as 1 over cosine t. And so if cosine of negative t equals cosine of t, then I could just replace this up here, right, with negative t, and also this up here with negative t, and this has to be the same thing as 1 over cosine t, which is secant t. And that's how I get this whole string of, that's how I calculated initially. I'm not sure like where to put this, but that's how I calculated this secant. And same thing for cosecant and all that. You would just do that. And if people want that seen out more, I guess let me know. Okay, but I am gonna, maybe I'll get rid of this part, but maybe I'll keep, maybe I'll rewrite it. Hold on. Let's see if I can do something funky. Does this? Oh, okay. We're getting crazy over here. Okay. Maybe I'll keep it like that, even though that's still pretty chaotic and unorganized. It's just a note. Note. Okay, and maybe I'll keep that there. Okay, so now we're going to use these properties of trig functions to simplify some things. And again, like, I mean, you should remember which ones are even and odd, but you don't have to memorize all of these things, because it's like, if you remember that it's even, it just means the negative is the same as the positive. And if you remember it's odd, it means you can pull that negative out. And so hopefully that is helpful, right? So this first one that we have, sine t, we're going to keep the same, sine t minus, but we can change this. It's either even or odd. So it's either sine t or it's negative sine t. And I remember sine is odd. So this is a negative sine t. And that means it's actually plus. So it's sine t plus sine t. And so it's 2 sine t. And that's our, and I remembered this, maybe I should say, sine is odd. So that's why we put the negative there. And you could skip that step and just automatically make it plus if you know like minus a negative, but I'm trying to show all of this here, right? So same things going here on this next one. Cosine is even. And that means that this is just cosine t. And so I bring this down, cosine t minus cosine t. Well, this just equals 0. This actually cancels out. It's a bit, seems a bit silly that you would even do that. And so now I have something a little more complicated. 3 sine of t. Well, I can't simplify that anymore unless I want to plug in a negative, but why would I make it more complicated? So 3 sine t plus, now I see 2 pi minus t. So I don't really know anything about this, so they're just trying to trick us here. But I know because, so going back up, and sorry if you're like copying this, but going back up, I know that sine of t plus 2 pi is sine of t, right? So I remember this. So looking at that, if I can manipulate this, which I think well, sort of can, right? I can say this is the same, this right here is the same thing, same as negative t minus 2 pi. And because I know before it said t plus 2 pi, but when we have t and we add any number, like remember when it was n, so maybe I should have gone up a little further. When it was n pi, it was somewhere, or maybe we never did this. I'm not sure. But here, like if in this part, if I was to add 2 pi, add another 2 pi, add another 2 pi, subtract a 2 pi, subtract a 2 pi, it's still the same, right? So as long as I start with t, that was what was important here. And so I could take this negative out and I could say this is the same as t minus 2 pi. And so this is sine of negative t minus 2 pi. And, except, okay, there is another way to see this and it makes a lot more sense, but let me continue with this and then I'll show you that other way. But then we know that sine is odd, right? And we know the period is 2. So sine is odd. So this, what happens here is the negative can come outside. So we get 3 sine t minus sine, and now we just have t minus 2 pi. And then we have that the period is 2 pi, and this is that part I was telling you. We could add or subtract 2 pi. It doesn't matter. This is still going to be the same thing as just sine of t. So now I have 3 sine of t minus sine of t, which is 2 sine t. And I have a better explanation for that first part, I think, or maybe a different explanation. So another way to think of is, let me, another way to think of just this part, right? So let's just think of this, is sine of negative t plus 2 pi, right? Now, we know that t, it doesn't matter what t is here. This is in the same form as, and I'm sorry, I'm going back and forth between these pages, but this is this. If it was a negative t, it doesn't matter. It's the same thing. Just replace, if you replace this with negative t, then this is negative t, right? Doesn't matter. So that's what we're doing. So we could have also done this and said, okay, oh gosh, where am I? Okay. We could have done this and said, okay, this is the same thing as sine of negative t. And then we could have just kept going. 3 sine of t plus sine of negative t, which because sine is odd, this is negative sine of positive t. So we would have eventually got there, but this is just another way to do it. And because all of these trig functions are so related, because they're so related, there's actually many ways that you can do a lot of these problems and get the right answer. Sometimes it's 3 extra steps. Sometimes it's 1 less step, so just keep that in mind. And if you think of another way, feel free to share, or just know, like, if you got the right answer and you're like, wait, I did that different than what she did, this is okay. This is fine. So yeah. Okay, cool. And so that was C. Now looking at part D, I see sine of negative t times secant of t minus tangent negative t. So again, here, I'm just going to use right away, I know sine of negative t and tangent negative t. I can just use these from above, right? I'm just going to do that right off the bat. So I'm going to say, this is just negative sine t, and this is secant t, and then minus a negative. So I'm just going to write plus tan t. Okay, so I skipped a step there, kind of, but if you want me to keep it minus a negative, just feel free to tell me that, and I can do that. Because I know I post these notes, so I don't know if that's better. Or maybe I can do something like this. This is negative t. And maybe I'll do this. Is negative sine t. Okay. And I'm writing parentheses. It doesn't matter if you do or not, but I think sometimes if it's negative t, it just makes more sense to write the parentheses, but you don't absolutely need them. Okay, so now I have something here. I'm close. I'm close to simplifying, I think, all the way. But I see secant, and I want all sines and cosines. Maybe I see a plus tangent, so maybe I'll leave that for now. You could change it to sine over cosine, but first I just want to simplify this secant right here. So to do that, I'm going to say negative sine t, and then secant is 1 over cosine. So I have this, and then I'll say plus tan t. But negative sine over cosine. Sine over cosine is just tangent, if you remember, right? So this actually becomes negative tangent t plus tangent t, which is just 0. And now we have simplified to the max. Okay, this last page is my favorite, probably, because it is finally what I've been talking to you guys about for forever. I mean, it's been a week, but it feels like it's been a year already. So maybe not to you guys, but I guess life is just, one of my puppies is sick. So I have slept probably 3.5 hours in the past 3 days. So we are just tired over here. But this is my favorite, the unit circle summarized. And like I said before in the past, if you memorize just this like section, if you just memorize all of these guys, all of these, if you just memorize that, you will notice a pattern, and then you basically have the rest of this memorized. Okay. So I'm just letting you know the first quadrant to me is the most important. We will look at everything, but if you can remember the first quadrant, you can get to the rest. Okay. And I'm saying this, I'm promising it, but you know, if it doesn't happen for you, I'm sorry. So let's take a look. Let's take a look. So what we want to look at first is maybe these values, like what's going on here, how do we get these? So if you take this first point, it's 1, 0. It's a unit circle, nothing special, but well, nothing very special, but nothing fancy. But if I take this point here and I kind of highlight my right triangle. So let's pretend I draw my right triangle. So now I have like, this is a right angle, like there's my right triangle, right? And I have a 30, this would be 60, right? 30 is a, oh, I'm lying, that this is 30, but the angle up here is 60, but they're labeling it this way. So maybe I shouldn't even say, but here's my right triangle, that can stay the same. And it is a 30, 60, 90. And I know that my radius here gets me out to my unit circle, which is 1. And I know what my other sides are because of that. So what happens here is this side normally, and let me remind you, in a, gosh, I probably did this really poorly, but okay, in a 30, 60, 90 triangle, we usually had a hypotenuse of 2, and then this side is 1, and this is like square root of 3. This is normally, I think I drew this right, or I might have mixed up the angles. I probably did. So let's pretend I didn't, but it's something like this. But if I divide each of these by 2, this is what I get on the unit circle. So this is 1, there's my radius. Then this side should be, let's see, opposite. This side should be 1/2, sorry, oops, 1/2. And this side should be square root of 3/2. So we're just dividing. So I guess maybe I did do that right. Something like this, right? So this is where these points come from. But again, you don't have to memorize these triangles. So that's not the point of what I'm doing here. You need to know, here's my point. And how amazing is this? This represents, oops, not sine, right? This represents the x, which is cosine of 30 degrees, or cosine of pi over 6. And then this guy here represents y, which is sine of 30 degrees, or pi over 6, right? So this is really cool because you can do this for each of these points, right? And we call them, so if we focus only on like sine or cosine, you could travel, it's 0, 1/2, √2/2, √3/2, 1. And then you'll see these repeat. Like it's √3/2 again, √2/2, 1/2, 0. Like literally they repeat, and then they're negative because y is negative in the rest of the angles. And x does the exact same thing, right? So you can kind of see this pattern. And if we look at like the next one, the 45, 45, 90, if we look at this triangle, that's kind of how we get these root 2 over 2 and root 2 over 2. Okay. Now there is a term that I'm not like the biggest fan of it, but I will write this out for you. There is a term that's called Scooby. It's called, I already spelled it wrong. It's called quadrantals or quadrantals. I honestly, I mean, I don't know why it's called this, but what that means is the quadrantals are the points, that's like the points on your X and Y axis that are separating the quadrants. So for these, that would be 0 and then 1. I'm just kind of trying to show you the pattern here. Then we have in between this, we have 1/2, we have root 2 over 2, and we have root 3 over 2, right? And if we focus solely on like these guys here, these happen for the 30, 60, 90 triangles, like right triangles, right? Or the pi over 6, pi over 3, pi over 2. But maybe I shouldn't put a dash, maybe like a comma. Oops. Okay. So those, if you notice, every single 30, 60, this is related to 30, 60, this is related to 30, 60, related to 30, 60. If you look at all of those, every single ordered pair is 1/2 and square root 3 over 2, and they're just flipped or negative or reversed or something like that. So there's your pattern, right? And I'm not going to tear up right on this too much, but, and then you have root 2 over 2, which this is for the 45-degree triangle, or isosceles. It's 45, 45, 90, right? But, or pi over 4. And this, you'll see every single time it's root 2 over 2, but you just have to figure out which one's negative and which one's positive, right? So this is kind of nice because that's the pattern. If you can figure this out, these things repeat. And on each of the quadrants, so like on every like red point here, right? It's 0 and 1. Or maybe -1, but you can figure that out, right? So these are related to all of the quadrantals, right? Every point that's on the X or Y axis dividing our quadrants. So, okay, maybe this is blowing your mind and it's amazing. Maybe you're just like, whatever, this is like, this will help me pass everything. I don't know. But this is going to be, I mean, from this point on, you want to be using this and looking at this like all of the time, right? Because when you're solving like the problems below that we're going to solve, when you're solving these, looking at the unit circle, it makes it much, much easier. And then eventually, like myself, like I forget it sometimes, right? Hey, Scooby, I forget it, but then I look at this now, and I mean, next class, it's just in my head again, and it's just there. And I think, oh, what are we at? 5 pi over 6. Oh, that's here. Like I can just think of it, right? And granted, I was saying the first quadrant is most important. This is true. But if you really are looking at it a lot, you're gonna memorize the whole thing without even knowing it, and then be like, what is happening with me right now? And I thought I didn't like math, and look at me, memorizing the unit circle. If somebody, and my math professors would always make a joke, or they thought they were so funny, and they would say, if somebody, pulled you aside on the street, or like grabbed you and tried to kidnap you and said, we're gonna take you if you can't name sine of pi over 2, like whatever, they would always say something like that. And I was like, that's funny, but also like if that happened, that's absolutely insane, right? So I mean, they should make a movie out of it or something, but I guess it would end quickly. But Yeah, my professors would always say things like this, and it just was really funny. And I never really got it. And now I'm like, oh, should I say that? Is that funny? Like, but yeah, but I'm I'm refraining tonight, I guess, just telling you a story instead. Okay. So now we just want to use our beautiful unit circle to calculate the following. And again, you have it here, but I strongly recommend that you write out at least the first quadrant for yourself, if not the whole thing. Write it on a piece of paper, color code it, make it pretty, make the cosine all blue, the sine's all green, like whatever, right? Because this is really going to help you also just to remember it. And maybe it's fun. Maybe you like coloring. I don't know. Okay. So looking at cosine of 5 pi over 4. So the beautiful thing about this unit circle here, I mean, when you have to have this memorized, you have to think a little bit more, but we can just go straight ahead to 5 pi over 4 and 5 pi over 4. And cosine I know is related to x. So it's negative root 2 over 2. So I don't even really have to think about that. I'm just going to say this is negative root 2 over 2. And I just have to know, you have to know. So although I'm saying it's not difficult, you have to know how to read this. So it is difficult because if someone who has never seen trig or never seen this before, they maybe could piece it together, but it would take them way too long and they'd also possibly get it wrong. So this is difficult. I shouldn't say it's easy. You need to be able to read it to understand what's going on. And there is a lot to it, right? So cosine of pi over 4, we've got sine of negative 2 pi over 3. This is where it gets a little tricky because they did not label negatives. And this is why making your own could be absolutely amazing. But here, let's do some negatives. So this, we know this, we start at 0. This would be negative pi over 6, negative pi over 4, negative pi over 3, negative pi over 2. Now I want to get to negative 2 pi over 3. Well, as soon as I have this first quadrant, just so you know, and you can see it with the positives, like if I look just at pi over 3, if I follow 0, pi over 3, 2 pi over 3, 3 pi over 3, that's just pi, right? 4 pi over 3. So there is a pattern here. And so if I'm following this negatively, it's the exact same pattern. So if I'm looking negative, I'm saying, okay, 0. Then I'm saying negative pi over 3. Negative 2 pi over 3 is going to be the next pi over 3 segment, right? So that's going to be this one. So this is negative 2 pi over 3. And that's what I was looking for. And now I have this point with that. So sine of that is what the y, right? So negative root 3 over 2. And you could, okay, I forgot. I mean, I was going to do this. You could also draw these out and say, okay, 5 pi over 4. Well, 4 pi over 4 is pi. Like you could also draw this out for yourself, like 0 pi. And I know 5 pi over 4 will be here. Like this will be 5 pi over 4. If you want to know, like, I mean, you have your unit circle, right? But if you wanted to just know for yourself, like where is that located? And you could draw it for yourself. And then if you relate it back to your unit circle, you know, you could figure out that, oh, this was root 2 over 2 or negative and negative root 2 over 2. Like there's that point. Same thing with negative 2 pi over 3. You could say, okay, if here was 0, here was negative pi over 3, then this is going to be negative 2 pi over 3. So maybe I should have just drawn this one. It would be something like this, negative 2 pi over 3. And then you'd look for that point and you could write it down. And this is just if you have your unit circle, but maybe it's on a different page, because right now this is all, I can literally see it all on one page. But if it was on a separate page and you were trying to figure this out, it could help to just write it and write the point. And then later, if you go back to that problem, instead of having to dig or like think about your unit circle, you could say, oh, there's the angle. That's what I was doing there. Like this makes sense, right? Okay, and the last one is 5 pi over 6. So let's think about where that would be. 5 pi over 6, just before just thinking about it, I know pi is 6 pi over 6. So it's going to be, you know, one of these here. It's going to be somewhere, I mean, that's not exact, but it's going to be somewhere here, 5 pi over 6. And then again, we're going to use our trusty handy dandy unit circle. I'm going to find 5 pi over 6. It's here. And I want what, tangent? Ooh, okay. So I want tangent. So I'm going to write this point out actually, because, so this is negative root 3 over 2 comma 1/2. Or wait, did I just mix that up? I totally did, didn't I? No. 5 pi over 6. Yeah. Okay. So this is the point. And remember, tangent is y over x or sine over cosine. So it's 1/2 over negative root 3 over 2. Now, you could simplify this right away and say, oh, I know these twos are going to cancel. Or you could say this is 1/2 times negative 2 over root 3, because I can just, when I divide by fractions, multiply by the reciprocal. And then my twos still cancel. Beautiful. And I'm left with negative 1 over square root of 3. And yes, I should rationalize that. So, ooh, this had a little bit of work, but we still had our nice unit circle to help us get there. Yeah. And this last question, maybe I'll move this over here for you guys. Yeah. So what is the range of sine and cosine functions? Okay, I mean, we discussed this earlier. Oh no, we didn't. We just discussed domain. We did not discuss range. So I'm going to say, recall the domain of sine and cosine is all real numbers. This nice big R, right? And we'll look at the general shape of this, but the range of sine and the range of cosine, they're actually going to be the same. They're very related, but you know, just not equal. And the ranges, if you think about it, looking at your unit circle, looking at all the points we have there, just focusing on sine, so just the y. If you take a look up here and you say, okay, you know, you say, oh, let's just do something different. So it's okay. So you just take a look at, or maybe we just take a look at the x's. So the cosine, you take a look at all of these numbers, they're between two main numbers, right? So I could keep going, but every single one is between two main numbers. And okay, before giving away, maybe, do you know what anyone know what those numbers are? It's between
1 and -1.
Yeah. And someone said 1. Yeah. And you're right. So like it's between 1 and -1. Yeah. Because we have the biggest number I see is 1. Granted, I think to myself, what's root 2 over 2? What's root 3 over 2? Well, if you did them as decimals, they're 1 point something. I mean, they're 0 point something, right? So, so these are all fractions. They're all smaller than 1. And then same thing with -1. So what our range is going to be here now, if I can get back to it, is going to be -1 to 1 for both sine and cosine. And it's on the unit circle. So like, because it's on the unit circle, that circle is forcing x and y to be smaller than plus or minus 1 or equal to, right? So yeah, and the general shape, we're going to see this later, but I'm going to attempt maybe to just draw this for you. Okay, so let's do this. So it's not going to look pretty. I'm going to try though. Let's see. And somebody said it earlier. Somebody said like sine waves or something like that. Okay, so pretend those are all even though they're totally not. But basically, you know, what's happening here is that this value will be 1, this will be -1, and this is the general shape of both sine and cosine. And notice how I didn't draw the, this is like the x-axis if you think of it, but I didn't draw the y-axis because it's in a different place for sine and cosine. It's just shifted, but they both look like this. And again, you could go to Desmos or Google and say, hey, and say, what is sine and cosine? Like, what does this look like? You know, and you could just Google the graph of it and see them all. And if you are super curious, I mean, feel free. I don't know. I don't think you have to graph in homework just yet. But yeah, but this is what that looks like. Okay, I'm gonna pause again here. Are there any questions? Anything pressing? Anything crazy? Scooby objects to all of the trig. Scooby is my barking dog. My other dog is being good.
I have a question.
Yeah, Veronica, go ahead.
So for C, it's, I guess when you're looking at like 5, 5, or 6, it's not just a matter of looking at the circle and seeing what corresponds. Like this one, you had to do something a little different.
Yeah, so for this one, the reason for that was because we were finding tangent, right? So remember that tangent of like theta or t. I guess I should stick to t. Hold on, I'm all torn up here. Tangent of t is sine divided by cosine. So I had to actually find, instead of just looking at it and saying, oh, it's this number, I had to find that, and then I can't leave my answer in this, right? So we had to simplify that. That's why it took a few extra steps. And that's also why I really love sine and cosine. They're a lot easier typically than every other trig function, because all of the other trig functions are related to sine and cosine.
Okay, thank you.
Yeah. Any other questions?